All right. Are the slides visible to you guys?
Yes, sir.
Yes, yes, yes.
Great.
Mechanical property part two.
GGG. Thank you. So we'll continue with this chapter on mechanical properties. We had looked into some of the properties in the first half. We'll continue exploring the mechanical properties. So with this continuation, we'll introduce you to ductility. How do we define ductility? We had looked into the stress strain plot of a ductile and brittle material, but what actually is the measure of ductility? It is the plastic tensile strain at failure. Again, it is something which relates to strain, something that relates to tensile test, and a property which is measured with regards to failure. So, if I have this tensile sample, initially the area is A naught and the length is L naught. And finally, if I apply tensile load onto this material, the final length at fracture is this total length. The length has increased, and the final cross-sectional area is this. The cross-sectional area has reduced. Now, if I have these four characteristics of the sample known to me, I can define ductility in terms of percentage elongation. How much the elongation took place as the sample uh, was subjected to tensile load and it ultimately fractured. So, how do you define percentage elongation? You define it by the difference between the final length minus the initial length divided by the initial length into 100%. This is percentage elongation for you. And if you look at the tensile stress strain plot, engineering tensile stress versus engineering tensile strain, you see that if you have lesser strain up till the fracture point, you would have smaller percentage elongation. Similarly, if you have a larger uh, strain up to the fracture point, you would have a larger percentage elongation, provided your maximum stresses are comparable. All right. There is one another way in which you can define the ductility of material. You use the dimension length to define the ductility of a material. You can also you can see that as the length was increasing, area geometric representation, which is area, is also changing with respect to the tensile load. So you could use another ductility measurement, which is percentage reduction in area, and percentage reduction in area is expressed as initial area minus final area divided by the initial area into 100%. Now, if you see, the initial area is having a larger value as compared to the final area. So this value would come out to be positive. Now, since the value is positive, you have already expressed that this value is expressing a reduction in area. All right. So a positive value is indicating the reduction in the cross-sectional area of the sample. Clear enough?
Yes, sir.
Yes, yes.
All right. Moving on, the term resilience. How do you define the term resilience? All right. Uh, it is the ability of a material to store energy. And when I say store energy, it is specifically referring to the energy stored within the elastic region. All right. So if you have a stress strain plot, the area under the curve of a stress strain plot basically represents energy, or energy per unit length, and up till the elastic limit, the energy stored is represented by area under the curve, and you refer to this energy as resilience of a material. How do you find out this energy? You just need to integrate from 0 to the strain up to the yield limit. From 0 to yield limit strain, stress is integrated with regards to the change in strain, and that would give you the area under the curve up till the elastic limit or the resilience of the material. Now, if I for this I need to have a relationship between stress and strain in order to integrate. If we have to simplify, I can assume this line to be a straight line. This is my assumption. And with this assumption, if I have a linear stress strain curve up till this point, I can simplify this with the area of a right angle triangle. So it would be half, this is the base, into height. This would give me the resilience of the material, which the units are stress, energy per unit volume. So the area under the stress strain curve is basically representing energy per unit volume. Clear enough so far?
Yes, sir.
All right, moving on. How do you define the toughness of a material? What is toughness of a material?
Sir, the stress
Sir,
it can
ability
bear.
of material to resist load, sir.
Ability of a material to resist load. Hardness is also an ability that resists load. Resilience is also an ability that resists load. So what's the difference between toughness and resilience?
Sir, it bears the stress. The ability of a material to bear the stress.
Stress. Stress is again nothing.
Fracture,
Sir,
sir.
elastic. Sir,
Sorry.
sir, इलास्टिक
Fracture.
लिमिट से आगे भी इलास्टिक
Sir,
लिमिट से आगे भी ये स्ट्रेस बर्दाश्त करती है
जी कहाँ तक करती है?
सर फ्रैक्चर लिमिट तक
जी, it is the energy required to break a unit volume of material. All right, it is approximated by the area under the stress strain curve. So it is the total energy that is required to break a unit volume of material. Again, if you have engineering tensile stress and engineering tensile strain curve, the total area under the curve of tensile stress strain sample would give you the toughness of a material. Ceramics, as you know, they are brittle. They would have smaller toughness. Metals, which have high plastic deformation, they would essentially have larger area under the curve. And all right, those unreinforced polymers, they would have, although much plastic deformation, but since the maximum stress is not that much, their toughness is uh, uh, not that much. Brittle fracture, you would essentially have the energy stored as elastic energy. Ductile fracture, you'll have both the components, elastic plus plastic energy, both contributing towards the total energy that leads to the rupture of the material. All right. Now, up till now, we have been dealing with engineering stress and engineering strain. How do you differentiate engineering stress with engineering strain, engineering stress with true stress? G, are you there?
यस सर बिलाल
Yes, sir.
G,
सर थोड़ा सा ऑफ टॉपिक है लेकिन
मुझे कुछ हॉस्टलाइट से मैसेज किए, एतजाज हॉस्टल का जो इंटरनेट है वो लैग है। तो
I'll get back to you. The internet in the college is not working at the moment. All right. So what they could do is that they could get back to the recording. All right. Those who are not
ठीक है
able
सर,
to attend the session, they can get back to the recording.
ठीक है।
All right. G. So what's the difference between engineering stress and true stress? No idea?
सर आइडिया तो नहीं है,
सर
लेकिन ये कह सकते हैं कि मतलब जो ट्रू स्ट्रेस है सर वो तो मतलब जो वो कंप्लीट वो बर्दाश्त कर सकता है, लेकिन वो सर इंजीनियरिंग के हिसाब से अगर वो जो मटेरियल बनाते हैं और उसको अपनी वो
अच्छा
स्ट्रेस
अच्छा
सेट करते
अच्छा
हैं जो
अच्छा all right. Before we go into how do you define engineering stress? Engineering stress is force over which area?
सर क्रॉस सेक्शनल एरिया होता है, फोर्स और क्रॉस सेक्शनल एरिया।
Original cross sectional.
ओरिजिनल क्रॉस सेक्शनल एरिया सर।
Very good.
तो सर फिर ट्रू स्ट्रेस में सर फिर होल एरिया ऑफ बॉडी होगा।
It is the instantaneous cross sectional area. All right.
यस सर, एक्चुअल कह लें।
The cross sectional area changes when sample is stretched, or so if I look at the true engineering stress curve जो है, जो कि हम मोस्टली यूज करते हैं, वो ब्लू कलर से शो हुई है, और जो रेड कलर की कर्व है, दिस इज द ट्रू स्ट्रेस स्ट्रेन कर्व. इफ यू सी अप टिल दिस पॉइंट, यहाँ तक कोई ऐसा खास फर्क नहीं आता. इस पॉइंट के बाद इफ आई लुक एट दीज 2 पॉइंट्स ओवर हियर, इस पॉइंट के बाद इफ आई लुक ओवर हियर, कर्व ऊपर जा रही है और एक कर्व नीचे आ रही है. Stress is force over area. All right. Is this clear? Stress is force over area.
यस सर।
All right. अगर एक्चुअली मैं देखूं, एक्चुअली मटेरियल के ऊपर जो स्ट्रेस लग रही है, इट इज दिस स्ट्रेस. ये स्ट्रेस की कोई वैल्यू है. This stress, which is true stress, is calculated based on force divided by instantaneous area or the area at this moment. Clear?
यस सर।
At this moment, AI, which is the instantaneous area, would it be less than or greater than the actual area?
सर लेस देन।
लेस देन सर।
So this would be less than the actual area, which is A naught. Now, if I calculate the same stress using an area which is A naught, would it be greater or less than this stress value?
सर इवेंचुअली इट विल लेसन हो जाएगा।
यस सर,
स्मॉलर हो जाएगा।
सर स्मॉलर होगा
क्योंकि फोर्स तो वही रहेगी ना. इफ आई डिवाइड द फोर्स बाय अ greater value of cross sectional area, which is the original area, I would essentially have a smaller value. Clear?
बिल्कुल।
ये चीज क्लियर है?
यस सर क्लियर है।
All right. So what is essentially happening is that in engineering stress strain curve, after the point where necking has formed, the cross sectional area reduces. So in actual, the stress is increasing, but when you calculate the stress based on original cross sectional area, which is the engineering stress strain curve, your curve basically shifts downward. Clear?
यस सर।
सर एक चीज बता दीजिए, ये ओरिजिनल क्रॉस सेक्शनल एरिया और एक्चुअल क्रॉस सेक्शनल एरिया।
जी इसमें क्या फर्क है?
सर एक्चुअल जो हम यानी ओरिजिनल तो वो होगा जो हम शुरू में हमने मेजर किया होगा, और एक्चुअल एट दैट पॉइंट इंस्टेंट पे
एक्चुअल वो होगा that is at that very instant. ये
ठीक
ओरिजिनल
है
क्रॉस
सर
सेक्शनल एरिया है, ऑलराइट।
यस
जैसे
सर
जैसे
ठीक
लोड लगाएंगे तो क्या होगा, ये क्रॉस सेक्शनल एरिया कम होना शुरू हो जाएगा क्योंकि ये
यस सर
स्ट्रेच हो।
डिक्रीज होगा
और ये सिग्निफिकेंट डिफरेंस कब आएगा, नेकिंग के बाद, जब यहाँ पे नेक फॉर्म होना शुरू हो जाएगी। दैट इज आफ्टर द मैक्सिमम टेंसाइल लोड, ऑलराइट।
यस सर ठीक है क्लियर
ठीक, ऑलराइट।
सर
नाउ जी,
सर इधर क्वेश्चन है सर, इधर हम टेंसाइल फोर्स अप्लाई करने से अगर कंप्रेसिव फोर्स अप्लाई हो तो एरिया तो थोड़ा ज्यादा होगा, तो फिर ये टू स्ट्रेस क्या होगा?
नो, आप बेसिकली कंपेयर कर रहे हैं इन टेंसाइल मोड्स में कंपेयर किया जा रहा है। यू डोंट एक्चुअली, तो आप ये ट्रू स्ट्रेस स्ट्रेन कर्व भी यूज नहीं करते। जो आप डिजाइन पर्पस के लिए यूज करते हैं, यू एक्चुअली यूज इंजीनियरिंग टेंसाइल स्ट्रेस स्ट्रेन कर्व, ऑलराइट, फॉर मोस्ट ऑफ द कर्व्स। वील सी हाउ, हम अभी देखेंगे कि हम कैसे यूज करते हैं इसको। बट you don't essentially use tensile stress strain curve or compressive stress strain curve. You essentially use engineering tensile stress strain curve for your design purpose, all right?
ओके सर।
आपको ये चीज समझ आई है?
यस सर।
And we'll come to see how. So compressive भी हो सकती है, you can have multi-axial load, but you don't need that. This is the simplest form of test that you can perform. तो इसी की बेसिस पे आप बेसिकली डिजाइन करते हैं बहुत से मटेरियल्स का। विल सी हाउ एनीवेज। सो हाउ डू यू डिफाइन द ट्रू स्ट्रेस? सिग्मा with a t in the subscript would define the true stress strain, true stress. And what is the true stress? True stress is force divided by the instantaneous cross sectional area, the cross sectional area at that given moment. Similarly, the true strain is epsilon having a subscript of t is defined by the natural log of instantaneous length, the length at that moment, instantaneous length divided by the original length. And if you want to convert, or if you want to have a relationship of true stress with engineering stress, it is this relationship. True stress is related to engineering stress multiplied by 1 plus engineering strain, and true strain is related to the engineering strain with the natural log. All right, are these relationships clear?
यस सर क्लियर
Right. So moving on, how do you define engineering strain? If let's say I have this block with me originally, if you see the width of the block is W naught, the original value of the width is W naught, and the original length is essentially L naught. All right. As I apply tensile load onto this material, after certain load has been applied, the material elongates in this direction and it contracts in the lateral direction. As a result of this, the deformation in the material is sigma, delta by 2 in this direction and delta by 2 over here. Similarly, the shrinkage in the lateral direction is delta L by 2 over here and delta L by 2 over here. Now, if I have to define the tensile strain, when I say tensile strain, I mean engineering tensile strain. Whenever I use tensile strain or tensile stress, this refers to engineering tensile strain or stress. So engineering tensile strain is basically the change in length, which is delta, divided by the original length, which is L naught. And along the, which is also called the longitudinal strain because this is along the longitudinal axis. If I have to define the lateral strain would be a reduction in this direction, reduction in the lateral direction, divided by the original length, which is the width W0. So change in the lateral direction divided by the width of the sample would define the lateral strain. Is this clear to you guys?
Yes, sir.
And there is a term that is used with these materials, which is Poisson's ratio, or V. How do you define Poisson's ratio, or V? It is the lateral strain divided by the longitudinal strain. That means how much of the increase in longitudinal direction has the decrease in the lateral direction taken place. Lateral strain divided by the longitudinal strain, and it is a dimensionless quantity because you have a ratio of strains. So if you see, if your sample is being stretched in the tensile direction or longitudinal direction, you would see a reduction in the lateral direction. Similarly, if your sample is compressed in the longitudinal direction, you will see a increase in cross-sectional area or increase in the width of the sample. So you'll have an opposite effect depending upon the way or the direction in which you're applying the load. Metals normally have the Poisson's ratio as 0.33. That means if the increase in longitudinal direction is 100 units, the decrease in the lateral direction would be 33 units. Generally, metals have this ratio. Ceramics 0.25 and polymers 0.40. All right. Now, moving on towards shear stress and shear strain. How do you define shear stress and shear strain? Shear stress, again, stress is force, a relationship of force and area. If you have this metal block with you and you apply the load along the area, parallel to the area. If you are applying force parallel to the area, in this way, you would essentially have a sample moving in this manner. So how do you define shear stress? Shear stress is basically the shear force, which is the parallel force acting on the surface of the material divided by the area on which it is acting. Is this clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
All right. All right. So if the shear stress is clear, how do you define shear strain? This yellow block is essentially showing the original sample. The black is the distorted one. Now, if you see the distortion that has taken place, if you have this black as the distorted region, this is the angle theta, which represents the distortion. This is the change in length, delta x, divided by the original length, which is y. So how do you define shear strain? You define shear strain by change in the x direction divided by the original direction or original length along the y direction. Shear strain is basically a measure of this angle, and this angle is basically expressed as tan theta. Since the angle is small, you can express it as tan theta, and this tan theta is essentially change in this direction delta x divided by the height of the sample or the length in the y direction. Clear? How do you define shear strain?
यस सर
Yes, sir.
सर ये वैसे स्लोप ही नहीं हो जाएगा tan थीटा वो जिस तरह
Obviously, it would be
Yes.
this slope. ये slope
Okay.
होगी. Alright.
Okay.
Again, this slope अगर ये ज्यादा है तो इसका मतलब है strain material के अंदर ज्यादा है, deformation ज्यादा है. अगर ये कम है तो इसका मतलब है कि deformation कम है. Again, it is indirectly representing deformation. Clear?
Yes, sir.
So strain जहाँ भी आता है, it is basically representing the deformation in the material, whether it's tensile strain or shear strain. Now, other common stress straits, I'll show you 3 images. Could you see which figure represents which state? Simple compression कौन सी state है, biaxial tension कौन सी state है और hydrostatic compression कौन सी state है?
सर पहली वाली जो आर्च है वो क्या कहते हैं सिंपल कंप्रेशन है, बाई एक्सियल जो है क्या कहते हैं सिलेंडर है और जो हाइड्रोस्टैटिक कंप्रेशन है वो फिश अंडर वाटर है.
Very good. So simple compression is where you have compressive load being applied. Note compressive structure member stress would be less than 0 since the direction is represented by the negative number. So if you see over here, these bars, they are in the compressive load. So simple compression is this one. Now biaxial tension is where you have stress acting in 2 directions and the stresses are greater than 0. So in the cylinder you essentially have stresses acting in 2 directions, longitudinal direction and the radial direction, and you have the surface of the cylinder in biaxial tension load. And if you see this example of fish underwater, you have this hydrostatic compression where the stress is acting uniformly in a compressive manner from all directions. All right. So these are other common states of stress. Now, if we talk about other elastic properties, these properties include shear modulus, which is modulus of rigidity. You have looked into E, which is the Young's modulus. The shear modulus is related to the shear stress. It is the relationship between the shear stress and shear strain, and it is represented by what? The slope of the linear region for a shear stress strain plot. Just like the Young's modulus, where you have engineering tensile stress and strain relationship governed by Young's modulus. So shear stress, shear strain, this is the constant of proportionality, which is the shear modulus. Elastic or elastic bulk modulus, which is defined by K, it is for the hydrostatic testing, जहाँ पे you have pressure acting in all directions, and due to this pressure, the initial volume, which is represented by black line, gets decreased to this final volume, which is represented by the green square. So you have initial volume and volume change. So bulk modulus or elastic bulk modulus is essentially related to the strain in the form of change in volume divided by original volume. So it's basically the deformation in volume that is being represented in bulk modulus. So you have force in the form of pressure and you have strain in the form of volumetric strain, and this is being represented in this form. Force is the pressure, stress is represented by the pressure, strain is represented by the volumetric change, and K is the proportionality constant, which is the elastic bulk modulus in this case. All right. So what I'll do is that let's